Neptune orbits roughly 2.8 billion miles from us. 1 year out there burns through 165 of ours. We told ourselves that being that far away meant the planet would stay still. That turned out to be a mistake. Over the past 20 years or so, Neptune's temperature crashed without any warning. Then its south pole abruptly flared with heat. And then, one by one, every cloud across the entire planet vanished. All of it gone. We are going to follow the whole chain of events tonight. The deep freeze, the sudden spike, the sky that wiped itself clean, and what every piece of it tells us about distant worlds far outside our own solar system. If you find yourself drifting along with this, drop a like and hit subscribe. It genuinely makes a bigger difference than you would think. Alright, let's get into it. Neptune sits at the outer fringe of the part of our solar system we like to think we know. It is so distant that light, racing along at 186,000 miles per second, needs more than 4 hours just to crawl out there and reach it. That same light touches Earth in roughly 8 minutes, so Neptune is not simply far. It belongs to an entirely separate tier of far. For nearly all of human history, no one even knew it was there. You could spend every clear night of your whole life staring upward and never catch a single glimpse of it. Every other planet the ancients could track, Mercury, Venus, Mars, Jupiter, Saturn, hung close enough to draw the eye. Neptune stayed buried in the dark, too faint, too remote, completely beyond reach of the naked eye. Without instruments that humanity would not build for centuries, the planet stayed hidden. And even once telescopes finally existed, nobody aimed them carefully enough at the correct patch of sky. Astronomers had their hands full cataloguing the things already in front of them, so Neptune waited. And here is the thing about going unnoticed for that long. When scientists at last began studying Neptune in earnest, they assumed it would cooperate. A slow world, a frozen world, a planet so far removed from the sun that anything dramatic seemed close to impossible. The sheer distance alone, they figured, should have rendered Neptune dull. Those two. 8 billion miles of separation mean the sun appears as nothing more than an especially bright star from Neptune's vantage point, delivering only a sliver of the warmth it pours onto Earth. Researchers expected a steady, frozen, utterly predictable place. That single assumption would end up costing them decades of bewilderment. The first genuine close look arrived in 1989, when NASA's Voyager 2 probe swept past after spending 12 years crossing the solar system. The pictures it beamed home were breathtaking. Brilliant white cloud bands streaking across a vivid blue atmosphere, a storm as large as Earth itself rotating in the southern half of the planet. Wind speeds so violent they broke every record the solar system had on file. Neptune looked untamed and fully alive. Nothing at all like the dead. Frozen marble scientists had sketched from afar, but Voyager 2 was only a flyby. It came through and just kept going. Scientists walked away with a single frame, not a movie. After that, watching Neptune meant straining through the finest telescopes available on Earth, stitching together scraps of data over the course of years. In 2003, a group of researchers launched a methodical campaign to monitor Neptune's temperature using thermal infrared cameras. These instruments pick up heat the human eye will never register. They allowed scientists to gauge exactly how much energy Neptune's atmosphere was shedding at various latitudes. The team would keep gathering measurements over the following 2 decades, assembling the picture one frame at a time, 95 images in total. What they anticipated our finding was a slow, sensible warming trend. Neptune had only just slipped into its southern summer back in 2005. Summer means more sunlight striking the South Pole. More sunlight should translate to more heat. The arithmetic was simple. The forecast was obvious. Go ahead and imagine a planet gradually heating up as summer takes hold. Smooth, steady, logical. That is the very last logical thing Neptune did. Because when the team lined up everything they had collected between 2003 and 2018 and studied the temperature curve, the line ran the wrong way. The planet was not heating up at all. The whole global atmosphere was getting colder. 15 years into a summer stretching across 40 Earth years, Neptune's stratosphere had plummeted by 14 degrees Fahrenheit across the entire planet. 14 degrees globally, in the middle of summer. Scientists had no framework that could hold that. Every model they had assembled, Every prediction they had committed to pointed in precisely the opposite direction. The planet that was supposed to warm up nice and slow had instead pulled the heat straight out of its own atmosphere and dumped it somewhere no one could locate. Something about Neptune was off, and the closer scientists looked, the stranger the whole thing became. Neptune's discovery counts among the oddest episodes in the history of science. Nobody actually spotted it first. A mathematician predicted it. In the 1800s, astronomers were carefully charting the movements of Uranus, the seventh planet. Uranus had turned up in 1781, and scientists took real pride in being able to pin down exactly where it should appear in the sky on any given night. Celestial mechanics, the mathematics governing planetary motion, was regarded as almost flawlessly understood by that point. Then Uranus started acting up. The planet kept sliding a little off the path predicted for it. Tiny departures hardly noticeable at first, but across the decades, the gap between where Uranus ought to be and where it actually showed up just kept widening. Something was dragging on it, nudging it sideways, an invisible gravitational pull that no known planet could explain. Two mathematicians, laboring separately and unaware of each other, landed on the identical conclusion. There had to be another planet out there, something massive, something far past Uranus, and its gravity was tugging on Uranus every time the two worlds drifted close enough to feel one another. Both men worked out where that hidden planet had to sit. They relied on nothing but mathematics, no telescope, no photograph, just equations describing gravity and orbital motion. They marked a point on a sky chart and said, "Look right there." In 1846, an astronomer swung a telescope toward that exact location. Neptune was sitting precisely where the math insisted it would be. One of the most remarkable predictions in the entire history of science, confirmed in the span of a single night. The accuracy of that forecast still impresses researchers to this day. These mathematicians had never laid eyes on Neptune. They had no image of it, no physical description, no means of confirming it was even real. They simply knew it had to exist, because the numbers left no other option. They trusted gravity over their own eyes, and gravity held up its end. But there is a twist in this story that rarely gets repeated. The astronomer who actually made the find, Johann Galle, only managed to locate Neptune so quickly because he happened to have a detailed star chart of that slice of sky. A chart someone else had drawn up just months earlier, mapping that region without the faintest idea a planet was lurking in it. Neptune had in fact already shown up on that earlier chart. It had been jotted down as a background star because no one was hunting for anything that moved. Neptune had been hiding in full view on paper for months before anyone recognized it as a planet. That detail says something about Neptune's character. This is a planet with a habit of sitting right under your nose while staying utterly mysterious. Even now, after Voyager 2's flyby, decades of telescope data, and the most sophisticated imaging humans have ever constructed, Neptune keeps inventing fresh ways to blindside everyone watching it. The 1989 flyby handed scientists their first true impression of what the planet looked like up close. Blue, turbulent, stormy, dynamic in ways that clashed completely with the cold, quiet world they had pictured. Sweeping cloud bands, enormous storms, winds faster than anything else in the solar system. And then almost immediately, scientists had to retreat to watching from billions of miles off. Voyager 2 had no reason to slow down. It was riding a trajectory that flung it straight through the outer solar system and onward into interstellar space. It never came back. Since that flyby, not a single spacecraft has returned to Neptune. Everything scientists have pieced together over the last 35 years had come from telescopes on the ground and in orbit, peering across 2.8 billion miles, trying to decode the faint signals a nearly invisible planet sends back in wavelengths of light no human eye can perceive. And what those signals began revealing after 2003 was something nobody had braced for. The planet was shifting quietly, rapidly, in ways that shattered the models scientists had spent entire careers constructing. The math had found Neptune once, but the math was nowhere near ready for what Neptune was about to do next. Step outside on a clear evening and look up. Pick out any star you can see. Odds are decent that a Neptunian year had already begun before that star reached the exact age it is right now. A single year on Neptune drags on for 165 Earth years. Sit with that image for a second. A child born at the instant Neptune kicks off a fresh orbit would grow up, grow old, and die before that same planet finished even one loop around the Sun. Their grandchildren might not survive to witness the finish line either. This is what happens when a planet swings around its star from 2.8 billion miles out. The circle it has to trace is gigantic, and Neptune ambles through that circle slowly, drifting along at something like 12,000 miles per hour. That sounds quick until you realize Earth tears around its much tighter orbit at 67,000 miles per hour. Compared to us, Neptune is sluggish, grinding through space at a crawl that makes its journey feel almost endless from any human point of view. The practical upshot of this is genuinely staggering. When Neptune was discovered in 1846, it had only just entered a fresh stretch of its orbit. The astronomers of 1846 never saw Neptune complete a single year. Neither did the astronomers of the early 20th century. It was not until 2011, a full 165 years after its discovery, that Neptune finally crossed back over the precise point in space where it had first been spotted. Scientists celebrated the first complete observed Neptunian year, even though every single person who had ever observed any portion of that year was long since dead. There is something deeply unsettling about a planet running on a clock that swallows entire human generations whole. And this timescale completely changes how scientists are forced to think about Neptune's behavior. On Earth, if you want to study seasonal cycles, you collect data over a handful of years. You watch spring chase winter, summer chase spring. You build up a library of repeating patterns. The cycles read clearly because you can observe many of them within a single career. On Neptune, one season alone lasts roughly 40 Earth years. A scientist who poured their entire working life, say from age 25 to 65, into studying Neptune's atmosphere would witness barely one full season from beginning to end, no repeats, no second pass through the same phase. Just one long, slow arc through a single chapter of Neptune's year, with no way of knowing whether what they recorded was ordinary or completely bizarre. This is the backdrop that makes the recent temperature readings so alarming. Scientists have been tracking Neptune's southern summer since 2005. They have something like 40 years of summer still ahead before the season turns. They are only in the opening chapters, and the planet has already pulled off several stunts that match nothing in any model. Every planet in the solar system runs on its own clock. Jupiter's storm systems churn for centuries. Saturn's rings shift across millions of years. But Neptune's pace puts it in a league of its own. Its changes play out on a scale that human institutions can barely span. The Voyager 2 flyby happened 35 years ago. 35 years is less than one Neptunian season. Scientists have never watched Neptune travel through even a full spring into a full summer in one unbroken stretch of observation. They have been building their models out of fragments of a story they have only just started reading. And buried inside those fragments, Neptune handed them a temperature record that demolished every assumption they held. Something was driving enormous changes inside a planet whose complete behavioral cycle no human has ever once watched from start to finish. A single season on Neptune lasts roughly 40 Earth years, 40 years. Let that settle for a moment. The Roman Empire at its peak endured somewhere around 5 centuries in total. One Neptunian season covers about 8% of that entire empire's lifespan. A streaming series gets axed after 2 seasons. A Neptunian season outlives most governments, most scientific careers, most human lives well into old age. This is the rhythm Neptune keeps. 4 seasons, each running 4 decades, cycling through a planet so distant from the Sun that every season is frigid by any standard a person would recognize. Even Neptune's summer is brutally cold by Earth's measures. But the difference between summer and winter on Neptune, that gradual shift in the angle of sunlight hitting the atmosphere over 80 years, produces changes in atmospheric energy that scientists are only beginning to grasp. Here is the basic machinery. Like Earth, Neptune sits on a tilted axis. The planet leans roughly 28 degrees relative to its orbit. Earth tilts at about 23.5, and that tilt is the reason we get seasons at all. When your hemisphere leans toward the Sun, You receive more direct light. Temperatures climb. Summer shows up. When it tilts away, the sunlight spreads across a wider angle and warms less. Winter follows. Neptune operates on the same principle. As it inches through its 165-year orbit, different regions of the planet slowly lean toward or away from the sun. The South Pole spends roughly 40 years tilted sunward, soaking up as much direct light as Neptune ever gets. Then over the next 40 years, the angle reverses and the North Pole takes its turn. The difference is that every stage of this process unfolds on a scale that makes Earth's seasons look like a flickering light switch. Neptune slid into its southern summer around 2005. The South Pole began its long, gradual lean toward the sun. Scientists expected steady warming. The models said, as the South Pole gathered more sunlight across the coming decades, temperatures in that region would rise slowly and predictably. That expectation shaped how researchers read their early data. When they started collecting thermal infrared readings in 2003, just before summer officially arrived, they were laying down a baseline. They wanted to document the opening of summer so they could measure the warming as it unfolded. What they actually recorded shredded that plan inside the first 15 years. The atmosphere did not warm. It cooled dramatically across the whole planet. A 14-degree Fahrenheit drop in the stratosphere globally during the opening decades of summer. Every single climate model ever built for Neptune had predicted the opposite curve. This matters for a specific reason. Scientists did not simply gather data and shrug. They had constructed detailed models grounded in decades of planetary science, atmospheric chemistry, solar radiation, and the documented behavior of other worlds. Those models existed to predict the future. The future arrived and looked nothing like the prediction. When a model that's confident collapses that completely, it forces a deeper question. Scientists were not merely wrong about one reading. Something fundamental about how Neptune's atmosphere absorbs and releases energy was operating differently than anyone had assumed. And then, just as researchers were starting to digest the cooling data and hunt for explanations, Neptune did something else entirely. Something that made the cooling look almost calm by comparison. In 2005, Neptune's southern hemisphere officially entered summer. Scientists saw it coming. They had been tracking the orbital arithmetic for years. They understood the geometry. As the South Pole tilted toward the sun, it would catch more direct light than at any moment in the previous 40 years. The atmosphere above the pole would soak up that energy. Temperatures would creep upward slowly and steadily, exactly the way summer works everywhere. The prediction stood on solid ground. It rested on the same orbital mechanics that govern seasons on every other planet in the solar system. The very same principles that let scientists calculate where a spacecraft will be in 10 years, or where a comet will pass in 100, these calculations work. They have been confirmed thousands of times across the solar system. For Neptune, the prediction was crystal clear. South Pole summer means more sunlight. More sunlight means more heat absorbed. More heat absorbed means rising temperatures. Scientists expected to watch the polar stratosphere slowly warm across the coming 4 decades as summer progressed. They had the instruments to measure it. The Very Large Telescope in Chile, along with the Keck and Subaru telescopes in Hawaii, all carried thermal infrared cameras sensitive enough to register temperature shifts across billions of miles. These observatories turned toward Neptune and started gathering data. The baseline readings from 2003 gave scientists a starting line. Everything was set up to watch a textbook planetary season unfold. A team led by researchers from several institutions assembled those observations into a long-running monitoring program. Every year brought new images. Every image added more data points. Over time, the thermal map of Neptune was supposed to display the summer warming as a clean signal climbing year after year across the southern regions. This sort of confirmation study seems almost routine in planetary science. You have a well-understood mechanism. You point instruments at it and watch the expected result play out. You are documenting something you already grasp rather than uncovering something new. The study was meant to be a confirmation, a record of summer settling over the most distant known planet. It became something altogether different. Because when scientists began analyzing the data seriously, and plotting temperatures across the full span of time, the warming curve they expected was simply not there. The line on the chart went downward globally across the whole planet. The stratosphere was bleeding heat at every latitude they checked. 15 years into a summer that should have been warming things up, Neptune was colder than when the season began. The scientists behind this discovery spent a long stretch of time checking their instruments. They revisited their calculations. They cross-checked data from multiple telescopes to make certain no single faulty sensor was feeding bad numbers into the results. The signal held steady across every instrument and every observing site. The cooling was real. A planet that orbital mechanics insisted should be soaking up more solar energy than it had in 40 years was instead shedding heat from its upper atmosphere at a rate that made no immediate sense. Something inside Neptune's atmosphere was overriding the simple logic of the seasons. Something was dragging heat away from the stratosphere and either locking it away elsewhere or venting it into space through mechanisms scientists had never modeled. They had no answer. They had only the data. And the data said Neptune was getting colder while summer was in full swing. The models built to describe this planet, the same ones that had survived decades of observation on other worlds, were failing on Neptune. And what happened next made that failure look like a warm-up act. Between 2003 and 2018, Neptune's global stratosphere dropped 14 degrees Fahrenheit. 14 degrees might sound minor when you are discussing a planet that already sits in the coldest corner of the solar system. But context flips everything. Think about Earth's climate. Scientists, governments, and researchers across every nation have spent decades raising alarms about global temperature shifts measured in single digits. A 2-degree change in Earth's average temperature threatens coral reefs, redraws coastlines, and destabilizes food supplies across entire continents. The difference between an ice age and the warm stretch we live in now amounts to roughly 9 degrees Fahrenheit averaged across the whole planet. Neptune's stratosphere shed 14 degrees globally in 15 years. On a planet where researchers had been expecting warming, that drop was seismic in scientific terms. It meant the upper atmosphere was releasing heat faster than it was absorbing it from the sun. The energy budget, the balance between what comes in and what goes out, was running an enormous deficit. The stratosphere is the layer sitting above the active weather zone. On Earth, it is the region above the clouds and the storms, the calm high band where commercial jets cruise. Neptune's stratosphere behaves differently, but the principle holds. It sits above the turbulent lower atmosphere and plays a central role in regulating the planet's overall energy balance. When the stratosphere cools, it reshapes how heat moves through the entire atmospheric system. A 14-degree global drop across 15 years is a signal that something is actively pulling energy out of that system. Scientists ran through the possible culprits. The sun was the first suspect. If solar output fell, Neptune would receive less energy and might cool as a result. But the sun's 11-year activity cycle does not produce drops large enough or sustained enough to account for a 15-year cooling trend of this size. Solar variability was real, but nowhere near sufficient. The next suspect was Neptune's own chemistry. The upper atmosphere holds gases like methane and a compound built from nitrogen and carbon called hydrogen cyanide, along with other molecules that absorb and emit heat. If the balance of those chemicals shifted, the atmosphere might grow more efficient at radiating heat outward into space rather than trapping it. This is called increased radiative cooling. The atmosphere, in effect, gets better at venting heat. But scientists could not confirm which chemical change triggered the shift, or what triggered the chemical change in the first place. Then there is the wild card no one likes to wave away: plain random variation. Chaotic weather systems operating on timescales longer than any human observation window. Neptune's atmosphere might simply swing through extreme temperature fluctuations as part of its ordinary behavior, and humans had never watched long enough to catch it before. The trouble with that explanation is the scale. A 14-degree global shift in 15 years is not minor turbulence. It takes a powerful and sustained mechanism to drain that much heat out of a planetary atmosphere over such a short window, especially while the planet is sliding into summer. Scientists were left holding a partial picture Real data, a strong signal, and no confirmed mechanism to explain it. And while they were still assembling that case, the planet handed them a second dataset, one that appeared to flatly contradict the first. A planet tilting toward the sun gets warmer. That is one of the most basic principles in all of planetary science. It applies to Earth, it applies to Mars, it applies to every tilted, orbiting world scientists have ever examined. So when Neptune's south pole began tilting toward the sun as summer arrived, warming was the expected outcome. The geometry demanded it. A pole bathed in sunlight for the first time in 40 years should soak up that energy. The atmosphere above it should respond. Instead, the planet cooled. Scientists had to face a head-on contradiction between observation and principle. The geometry was correct. Neptune was entering summer. The South Pole was leaning sunward. The mathematics of orbital mechanics, the same mathematics that correctly predicts everything from solar eclipses to spacecraft trajectories, said warming had to follow. But the thermal data said the opposite. Something inside Neptune's atmosphere was actively fighting against what the sunlight was trying to do. To grasp how unusual this is, imagine if every summer on Earth the average global temperature dropped by several degrees instead of climbing, and nobody could explain why. Oceanographers would point at currents, atmospheric scientists would point at cloud cover, geologists would point at volcanic activity. Everyone would propose mechanisms, but none would fully account for the scale of what was happening. That is the spot scientists found themselves in with Neptune. The stratosphere is partly transparent to certain kinds of solar radiation. It does not absorb all the energy the sun delivers. Some passes straight through and warms the lower atmosphere directly. Some gets captured by specific gases at specific altitudes. The balance of that absorption depends on which gases are present and in what amounts. If the makeup of Neptune's upper atmosphere shifted between 2003 and 2018, the stratosphere might have grown better at letting heat escape into space, rather than holding onto it. A change in methane concentration, for instance, would alter how much infrared radiation the atmosphere traps versus releases. Methane absorbs heat. Less methane means more heat slips away. Nobody could confirm whether methane levels actually changed. Pinning down precise atmospheric chemistry across 2.8 billion miles is extraordinarily difficult. The measurements that exist are incomplete. The gap in the data is real. What scientists could state with confidence was this: Neptune's stratosphere got 14 degrees colder during a stretch when solar energy reaching the South Pole was on the rise. That does not happen by accident. Something drove it. The cooling was also uneven in a particular way that piled on another layer of confusion. The southern tropics, the mid-latitude band between the equator and the South Pole, showed a pattern of cooling, then slight recovery, then renewed cooling across the observation period. That kind of fluctuation hints at competing mechanisms at work, some pushing heat down, others pushing it back up, with the net result landing on an overall loss. This uneven pattern rules out one clean explanation. If a single simple mechanism were responsible, the temperature curve would be smooth. The jagged pattern suggests something more tangled, multiple atmospheric systems interacting with one another in ways no existing model had accounted for. Scientists were staring at a planet defying basic seasonal logic. They had the data, they had the mystery, they did not have the answer. And then Neptune did something that made the cooling look almost straightforward by comparison. Temperature data from Neptune's southern tropics between 2003 and 2018 told a story that flatly refused to fit any single explanation. The temperatures did not just fall and stay down. They dropped, then climbed a little, then dropped again. A pattern that looked almost like breathing, if breathing happened over the span of years and every exhale bled heat into space. This sort of irregular fluctuation matters for one specific reason. It means scientists cannot point to a single event or a single cause. A sudden atmospheric change would produce a sharp drop followed by a new stable level. A gradual ongoing process would produce a smooth, continuous decline. The pattern scientists actually saw, with its dips and partial rebounds, suggests several mechanisms running at once and occasionally working against each other. To picture it, imagine a room with two systems controlling the temperature, one air conditioner and one heater, both running at variable power, neither one talking to the other. The room temperature would swing up and down in a pattern that reflects the fight between the two systems rather than the behavior of either alone. That is roughly what the southern tropics data implies about Neptune's atmosphere. Planetary scientists call this kind of competing process internal variability. It means the atmosphere is generating its own chaotic fluctuations independent of outside factors like solar input. Every thick, complex atmosphere does this to some degree. Earth's does it constantly. The global temperature record shows short-term swings layered on top of longer trends. But on Neptune, the scale of that internal variability appears far larger relative to what the models predicted. The swings are wider, the recovery phases are weaker. The overall trend through the observation period stays firmly downward despite the partial rebounds. Scientists wrestled with a specific methodological problem here. Neptune's observation record, while detailed by the standards of outer planet science, is still short. 95 thermal infrared images spread across roughly 20 years is an impressive dataset for a planet 2.8 billion miles away, but 20 years is half of one Neptunian season. Researchers are trying to understand the behavior of an atmospheric system whose characteristic timescales may run far longer than anything they have managed to observe. A weather pattern on Neptune might unfold over 30 years. A climate cycle might span an entire Neptunian season of 40 years. Scientists observing through a 20-year window might be catching one phase of a much larger oscillation without being able to see the full shape of the wave. This is one reason planetary scientists stay cautious about committing to any single explanation for the cooling. The data is real, the cooling is confirmed, but the mechanism behind it stays unclear because the observation window may simply be too short to reveal the whole picture. That uncertainty is frustrating, but it matters. It is the difference between a mystery that needs more data and a mystery that exposes a fundamental gap in the models. Neptune's uneven cooling pattern points toward the latter. The models built on decades of planetary science never predicted internal variability at this scale. Something about how Neptune manages its energy budget is different from what scientists assumed. And while researchers were assembling that case, trying to make sense of the uneven cooling, a completely separate and far more dramatic signal surfaced in the data from 2018 to 2020. The South Pole had not been cooling. The South Pole had been doing something no one anticipated. While the rest of Neptune was losing heat, the South Pole had been building toward an explosion. In just 2 years between 2018 and 2020, the stratospheric temperature at Neptune's South Pole shot up by 20 degrees Fahrenheit. A single location on a planet that was globally freezing had suddenly and violently overheated. 20 degrees in 2 years, at a pole entering its first summer in 40 years. For reference, consider what 20 degrees of temperature change means in human terms. The gap between a comfortable 60-degree day and a 40-degree cold snap is 20 degrees. The gap between water as a liquid and water as ice is 32. 20 degrees is a massive full-body kind of change. On a planetary scale, at stratospheric altitudes, gaining 20 degrees in 2 years is extraordinary. Scientists had no recorded precedent for rapid, localized polar warming like this on any outer planet in the solar system. Gas giants like Jupiter and Saturn have storm systems and jet streams that create regional temperature swings. But a spike of this speed and magnitude at a pole was something new. The warming was tightly confined to the South Pole region. It did not spread gradually across the planet. It spiked in one area while the surrounding latitudes stayed cold. This created a sharp temperature boundary, a zone where the scorching polar stratosphere met the freezing atmosphere of the rest of the planet. Imagine setting a lit stove burner down in the middle of an open ice rink in winter. The burner glows hot. The ice 5 feet away stays frozen solid. The gap between those two temperatures exists in the same space, separated by no wall at all. That is roughly what Neptune's atmosphere was doing. Extreme heat and extreme cold sharing the same planetary system, divided only by latitude. This kind of temperature contrast drives atmospheric circulation. Hot air rises, cold air sinks, and when they meet along a sharp boundary, you get powerful wind systems. On Neptune, where winds already hit 200 miles per hour under normal conditions, a temperature boundary this sharp would generate atmospheric dynamics that scientists are still struggling to model. The timing made the spike even harder to explain. The South Pole had been part of the globally cooling stratosphere through the entire observation period up to 2018. Then, in the very same 2-year window, it reversed completely and rocketed upward by 20 degrees while the planet around it kept cooling. One possible explanation involves solar energy accumulation. As the South Pole spent more and more time tilted toward the sun through the summer season, solar radiation may have been slowly building up in the polar atmosphere in ways that did not immediately register in the temperature record. Then, at some threshold, that stored energy released rapidly, driving the sudden spike. But this explanation requires a mechanism for storing and then abruptly releasing atmospheric energy at a very specific location, and scientists have not confirmed what that mechanism is. Another possibility involves changes in the chemistry of the polar atmosphere, a shift in gas composition that suddenly altered how much heat the polar stratosphere could trap. But again, the precise chemistry is not confirmed. What is confirmed is the temperature record itself. The spike was real, it was fast, it was localized, and while the pole was overheating, something else entirely was happening to the visible face of the planet. The speed of Neptune's polar temperature spike has no real parallel in the history of outer planet science. To appreciate what 20 degrees in 2 years means on a planetary scale, you need a comparison point. Earth's climate responds slowly to changes in solar energy. Even during the most rapid warming events in Earth's geological record, global temperature shifts of this size took decades or centuries. The current warming on Earth, which has set off global alarm, amounts to roughly 2 degrees of average change over more than a century. Neptune's south pole gained 20 degrees in 24 months. Mars experiences polar temperature changes as its ice caps grow and shrink with the seasons, but those shifts are gradual and follow predictable, sun-driven patterns. Jupiter's atmosphere generates massive storms, but the temperature variations inside those storms are localized and short-lived. Saturn's poles show some warming during summer, but at a pace that climate models handle without difficulty. Nothing in the entire catalogue of outer planet observations prepared scientists for a polar stratospheric spike of this speed. One way to grasp the significance is to think about heat as a kind of pressure system. In an atmosphere, heat does not just sit in one place. It moves, it spreads, it drives circulation. A sudden injection of 20 degrees of heat into a polar stratosphere over 2 years means an enormous amount of energy arrived at that location in a very short time. Energy does not appear out of nothing. It has a source. Either more solar radiation suddenly reached the South Pole stratosphere than before, or a chemical process inside the atmosphere began releasing stored energy rapidly, or heat from deeper in the atmosphere rose and concentrated in the polar region. Each of these demands a specific mechanism. None of them has been confirmed for Neptune's 2018 to 2020 polar event. The James Webb Space Telescope, launched in late 2021, is now capable of analyzing the chemical makeup of Neptune's atmosphere in far greater detail than any earlier instrument. Scientists hope future observations will capture the chemical fingerprint of whatever process drove the polar spike. If a shift in gas concentrations at the South Pole can be documented, it could reveal the mechanism. But the spike itself happened years before Webb came online. Scientists have the temperature record and the mystery. They are still assembling the tools to solve it. What makes this particularly significant is the combination of the global cooling and the polar spike happening over the same period. The planet globally lost 14 degrees over 15 years. Then a single region at the South Pole gained 20 degrees in 2 years. These two events were unfolding on the same planet at the same time in opposite directions. Either these events are connected and one drives the other, or they are independent, and Neptune's atmosphere is capable of producing simultaneous extreme events at different scales and locations. Both possibilities are unsettling for the same reason. Neither one was in any planetary model, and while scientists were struggling to reconcile these temperature extremes, they realized the thermal data was only part of the story. Something visible was happening too. something anyone with a telescope could see, or rather, could no longer see. The temperature map of Neptune between 2018 and 2020 was one of the most extreme contrasts ever recorded on a single planetary body. The South Pole sat at the center of a scorching stratospheric hotspot, 20 degrees warmer than it had been just 2 years earlier. The rest of the planet stayed buried in its 15-year cooling trend, the coldest it had been since scientists started measuring. This is not a typical planetary temperature pattern. On Earth, the poles are the coldest places. The tropics sit closest to the sun's direct heat and stay warm. The temperature gradient runs in a smooth curve from the warm equator to the cold poles. It varies by season, but the basic shape stays predictable. Neptune flipped that logic on its head. A single pole burned hot while the latitudes between the pole and the equator sat in the coldest stretch on record in modern observation history. To picture the contrast, imagine a football field blanketed in snow from one end zone to the other. Now imagine a blowtorch sitting at the center of one end zone, surrounded by snow, burning at full heat while everything beyond its immediate radius stays frozen solid. The end zone is scorching, the rest of the field is ice. That is Neptune's temperature profile during this period, scaled up to a planet the size of nearly 60 Earths. The circulation patterns this contrast would drive are difficult to model accurately. Atmospheres respond to temperature differences by moving air from hot zones to cold zones. The sharper the temperature difference, the more violent the movement. Neptune already holds the title for the fastest winds in the solar system, reaching 2,200 miles per hour. A temperature contrast this extreme, sitting between the pole and the rest of the planet, would generate circulation dynamics that dwarf even normal Neptunian wind patterns. Scientists working on atmospheric models for Neptune kept running into the same wall. The models were built on assumptions about how heat distributes across the planet. Those assumptions came from observations of other worlds, from Earth's well-studied atmosphere, from gas giant data collected over decades. Neptune's actual behavior violated those assumptions at the most fundamental level. The hot pole, cold planet configuration also raised questions about what was happening in the lower atmosphere, beneath the stratosphere where scientists were measuring. The stratosphere is the upper atmosphere. What was going on in the weather layer below it during this period is harder to measure and far less well documented. The temperature extremes visible at stratospheric altitudes were probably driving unusual dynamics in the layers underneath. But scientists could not directly observe those layers well enough to say what. The contrast also raises questions about Neptune's seasons going forward. The South Pole will stay in summer for roughly another 25 years. If the polar spike was driven by solar energy accumulation, the pole may keep warming, or it may have already peaked and begun cooling back toward the global average. Scientists do not yet have enough post-2020 thermal data to know which way the pole moved after the spike. What they do know is that a planet behaving this way on the inside would also show signs on the outside, and the outside had already begun telling its own story. For most of human observation history, Neptune looked like a blue sphere streaked with bright white. The clouds were defining. Every major telescope image from the late 1980s onwards showed them, brilliant streaks of white swirling across a vivid, deep blue background. The Voyager 2 flyby in 1989 captured them in stunning detail, long wispy bands at high altitude and compact bright knots at lower levels. They gave Neptune character. They made it look alive. These clouds were not made of water the way Earth's are. They formed from methane ice crystals high in Neptune's atmosphere. Temperatures drop cold enough to freeze methane gas into tiny, solid particles that gather into visible cloud formations. These methane ice clouds sit at altitudes where they catch sunlight and reflect it brightly against the planet's deep blue background. The blue background itself comes from methane too, specifically from methane gas in the lower atmosphere absorbing the red end of the sunlight spectrum and reflecting the blue portion back outward. So the blue comes from methane gas, and the white clouds come from methane ice. The entire visible face of Neptune is a methane story. When the Hubble Space Telescope began regular monitoring of Neptune in 1994, it documented those clouds in detail over the following years. They shifted and changed with the seasons and the weather. Some years showed more cloud activity, some less, but the overall presence of bright white features on the planet's face stayed consistent through the 1990s, the 2000s, and into the 2010s. The clouds were part of the expected picture of Neptune. Students learning about the solar system saw images with those cloud bands. Planetary science textbooks described them. Scientists built atmospheric models that included them as a normal feature of Neptunian weather. Ground-based observatories tracked the clouds too. Keck, Subaru, and the other major telescopes contributing to Neptune's long-term monitoring all recorded the bright features regularly. The data showed variations, busier years and quieter years, but always some cloud activity present. In the context of the temperature changes happening in the stratosphere above, the cloud behavior offered a potentially related signal. The clouds sit below the stratosphere in the active weather layer. If the stratosphere was cooling dramatically, that thermal change might influence the conditions that allow methane ice clouds to form. But the disappearance, when scientists finally assembled the full 26-year photographic record and traced the long-term trend, happened on a timeline that caught everyone off guard. The clouds were not just varying year to year. They were declining, gradually at first across the years following 2015, and then rapidly. By 2019, the cloud activity had dropped to nearly zero. A planetary feature present in every major observation for 3 decades was gone, and nobody had flagged it in real time because each individual observation looked like a quiet year rather than part of a collapse. The disappearance only became clear when someone stepped back and looked at the whole record at once. The disappearance of Neptune's clouds was not something anyone caught in real time. It was discovered the same way you might notice your height stopped changing, only by looking at a line chart of measurements taken over years. Individually, each data point looks unremarkable. Together, they reveal a trend that changes everything. A team of researchers collected and analyzed every usable telescopic image of Neptune taken between 1994 and 2020, 26 years of photographs. The archive included images from the Hubble Space Telescope and from ground-based observatories. Each image captured Neptune's cloud brightness, a measurable quantity that reflects how much white reflective material was present in the atmosphere at that time. When researchers plotted the cloud brightness numbers across those 26 years, a pattern emerged that nobody had clearly seen before. The brightness values fluctuated year to year, which was expected, but layered underneath those short-term variations was a long-term decline, a slow drift downward in the average cloud brightness that accelerated sharply after 2015 and reached a near-zero level around 2019 and 2020. Seeing it in the full 26-year record made it undeniable. The trend was real, sustained, and steep by the end. This kind of retrospective discovery is common in science. Individual observers watching Neptune in any given year have no access to the full record. They see that year's images and compare them to the previous year or two. A gradual decline happening over a decade looks like normal year-to-year variation when you are only looking at short windows. The signal only becomes clear when you zoom out far enough to see the full shape. The 26-year archive gave scientists that zoom, and what it showed was a planet that had been systematically losing its clouds across an entire generation of human observation. The timing connected directly to what scientists already knew about Neptune's temperature changes. The stratospheric cooling began around 2003. The cloud decline accelerated noticeably around 2015 and turned severe around 2019. The two trends overlapped in time, hinting at a possible connection between the cooling upper atmosphere and the disappearance of the lower cloud layer. If the stratospheric cooling reshaped the thermal structure of the atmosphere below it, it might have disrupted the conditions that let methane ice crystals form at cloud altitudes. Warmer conditions at cloud-forming altitudes, even a relatively small shift, could prevent methane from freezing into the ice particles that make up the clouds. The clouds would thin and eventually vanish. But the exact mechanism linking stratospheric temperature to cloud formation involves complex atmospheric chemistry that scientists have not fully mapped for Neptune. The connection is plausible and the timing lines up, but the direct causal chain is not confirmed. What the data does show clearly is that two major atmospheric features, the global temperature and the cloud coverage, both change dramatically over the same extended period. That overlap is too consistent to dismiss, and when scientists began searching for a third factor that might explain both changes at once, they stopped looking at Neptune and started looking at something much closer to home. When Neptune's clouds disappeared, the planet's appearance changed in a way that startled everyone who saw the images. Hubble Space Telescope photographs from 2020 showed a planet that looked almost completely featureless, a smooth, uniform blue sphere. No white streaks, no bright knots, no visible storms or atmospheric texture of any kind, just blue. The transformation from the cloud-streaked Neptune of the 1990s and 2000s to the bare blue marble of 2020 was striking. Scientists who had studied the planet for decades described it as looking stripped, as if something had been removed. That description is literally accurate. The methane ice clouds that had given Neptune its textured, active appearance for as long as modern telescopes had watched it were gone. The upper atmosphere was still there. The methane gas was still there, giving the planet its blue color. But the process that turned some of that methane into ice crystals and lifted them into visible cloud formations had essentially stopped. A blank Neptune carries specific scientific meaning beyond its visual strangeness. Clouds are active participants in atmospheric circulation. They reflect sunlight back into space, which affects how much solar energy the planet absorbs. They release heat when they form and absorb heat when they evaporate. They mark the locations of updrafts and storm systems. When the clouds vanish, scientists lose one of their main visual tools for tracking what the atmosphere is doing. A featureless Neptune is harder to read. The atmospheric dynamics continue below the surface of what telescopes can see, but the visible markers that helped scientists follow those dynamics are absent. The disappearance also carries a longer-term implication for the planet's energy balance. Without clouds reflecting sunlight, more solar radiation reaches deeper into the atmosphere. This could contribute to warming in the lower atmosphere, even while the stratosphere above it was cooling. The interplay between these layers is complex and not yet fully modeled for Neptune's specific atmospheric composition. Scientists also noted that the cloudless state coincided almost perfectly with the bottom of the solar activity cycle. The Sun in 2020 was near its solar minimum, the quietest point in its 11-year rhythm. This observation planted a seed for a new hypothesis, one that would shift the entire investigation in an unexpected direction. If something about the Sun's activity cycle was connected to Neptune's clouds, that connection would have to work across 2.8 billion miles of space. It would have to transmit an influence from a star to a distant planet through a process operating on an 11-year clock that matched the observed cloud cycle. That seemed almost too clean, too coincidental. But when scientists tested the timing carefully, the match held up better than they expected. Something the Sun was doing, something that changed on an 11-year cycle, appeared to be controlling whether or not Neptune had clouds. And the mechanism that makes that possible is stranger than it sounds. The Sun runs on an 11-year cycle. Scientists call it the solar cycle. At its peak, called solar maximum, the Sun erupts with flares, hurls charged particles into space, and floods the solar system with intense ultraviolet radiation. At its minimum, the Sun goes quieter, producing less radiation, launching fewer flares, and sending out a weaker stream of energy. This cycle shapes conditions across the entire solar system. On Earth, solar maximum can disrupt satellite communications, power grids, and navigation systems. Auroras glow brighter. The upper atmosphere expands slightly. The effects are real and measurable despite our relatively close distance. Neptune sits 2.8 billion miles away. At that distance, the Sun looks like a bright star, not the overwhelming disk we see from Earth. The total amount of sunlight reaching Neptune is roughly 900 times weaker than what reaches our planet. Scientists assumed this enormous distance would dilute the Sun's 11-year cycle to near irrelevance for Neptune's atmosphere. That assumption was wrong. When researchers overlaid the solar activity record against Neptune's cloud brightness data from the 26-year photographic archive, a pattern jumped out. Neptune's clouds were more abundant during periods of high solar activity, and less abundant during solar, quiet periods. The correlation was not perfect, but it was consistent enough to be statistically meaningful across multiple solar cycles within the observation window. The gap between solar maximum and the response in Neptune's cloud cover was roughly 2 years. Solar activity would peak, and then about 2 years later, Neptune's clouds would reach their highest abundance. The lag makes sense. Ultraviolet radiation from the sun does not instantly rearrange atmospheric chemistry. It triggers slow chemical reactions that build up over months and years before producing a visible result. The connections suggested a specific mechanism. Ultraviolet light from the sun was driving photochemical reactions in Neptune's upper atmosphere, the same way sunlight drives chemical reactions in Earth's ozone layer. These reactions were producing or activating compounds that served as seeds for cloud formation. When ultraviolet input was high, the cloud factory ran at full speed. When ultraviolet input dropped during solar minimum, the factory slowed or stopped. This is called photochemical cloud formation, and it is a known process in planetary atmospheres generally. But detecting it operating across 2.8 billion miles on a timescale tied to the sun's 11-year rhythm was genuinely unexpected for Neptune. Also raised a new set of questions. If the solar cycle drives cloud abundance, what else does it influence? Could the 11-year cycle also be contributing to the stratospheric temperature changes? The cooling that began around 2003 might overlap with specific phases of the solar cycle. If solar ultraviolet radiation also affects how Neptune's stratosphere manages heat, a drop in solar activity could contribute to the cooling trend. But scientists are careful here. The correlation between solar activity and cloud cover is a strong signal in the data. The connection between solar activity and the deeper stratospheric cooling is far less certain. The temperature swings are large enough that they may require additional mechanisms beyond the solar cycle alone. And then there was still the most dramatic event of all, the polar spike of 20 degrees in 2 years, which happened during a period of recovering solar activity. The timing there is messier and harder to explain with the solar cycle alone. The sun, it turned out, was part of the story, but only part. Here is how Neptune makes clouds. Sunlight, specifically ultraviolet radiation, travels 8 billion miles across space and slams into the top of Neptune's atmosphere. Down on Earth, ultraviolet light is the stuff that causes sunburn and gets blocked by sunscreen. On Neptune, the same kind of radiation acts as a trigger for a chain of chemical reactions that most people would never expect from a frozen blue planet. Neptune's upper atmosphere contains methane. When ultraviolet radiation strikes methane molecules at high altitude, it breaks them apart. The fragments then react with nitrogen and hydrogen molecules nearby, building new and more complex chemical compounds. One of the products of this process is a group of haze-forming particles called tholins, reddish-brown organic compounds that form in cold atmospheres under radiation exposure. Tholins are known to exist on other outer solar system bodies, including Saturn's moon Titan. These particles, along with other photochemical products, drift down through the atmosphere as tiny solid specks. At a certain altitude, temperatures drop cold enough for methane gas to freeze onto the surfaces of these particles. The methane ice coats the particles and builds up until you have a collection of small, bright crystals clustered together. Those clusters are Neptune's clouds. The process requires 2 ingredients in the right conditions at the right altitude. First, the photochemical particles produced by ultraviolet radiation provide the seeds. Second, cold temperatures at cloud altitude allow methane to freeze onto those seeds. Both have to be present. When solar activity is high and ultraviolet radiation is intense, more photochemical seeds form in the upper atmosphere. More seeds mean more nucleation sites for methane ice to crystallize. More crystals mean more clouds. When solar activity drops and ultraviolet intensity falls, fewer seeds form. The existing particles may linger for a while, but new seed production slows. Eventually, the supply of nucleation sites drops low enough that methane ice cannot form clouds efficiently. The existing clouds thin and disperse. The atmosphere clears. This process is called photochemical cloud seeding, and it explains why Neptune's cloud abundance tracks the solar cycle with roughly a 2-year lag. The lag comes from the time it takes for ultraviolet radiation to drive photochemical reactions, produce the particles, allow them to drift down to cloud-forming altitude, and then allow methane ice to build up on their surfaces. The mechanism also explains why the clouds disappeared so dramatically around 2019 and 2020. Those years coincided with the deep solar minimum, one of the quietest stretches for the sun in the observation window. Ultraviolet output dropped. The seed production in Neptune's upper atmosphere slowed dramatically. Without seeds, methane ice had no surface to grow on. The clouds stopped forming. Understanding this process is a major step forward for Neptune science, but it also opens a deeper question. If the cloud factory is this sensitive to the sun's 11-year cycle, what other parts of Neptune's atmosphere might the solar cycle influence? Scientists know that ultraviolet radiation affects atmospheric chemistry broadly. The same reactions that produce cloud seeds also produce other compounds that absorb or emit heat. If solar activity changes the concentration of these heat-active compounds, it might also alter how efficiently Neptune's stratosphere radiates energy into space. That connection between the solar cycle and the stratospheric cooling is the piece the models most urgently need to explain, and it remains an open question, one whose answer may reshape how scientists think about every planet at the edge of a solar system. In 2019, the Sun was near the bottom of its 11-year cycle, solar minimum. Ultraviolet output had been declining for several years, sliding toward its quietest point in the modern observation record. And 2.8 billion miles away, Neptune's upper atmosphere was responding. The photochemical reactions that produce cloud seeds were running slower. The ultraviolet input that drives those reactions had weakened. The stream of seed particles drifting down through the atmosphere toward cloud altitude was thinning, and without enough seeds, methane ice crystals had no surfaces to grow on. The clouds stopped forming. Telescope images from 2019 showed a Neptune visibly different from any image in the 26-year archive. The bright white features that had been present to some degree through every previous year of observation were nearly gone. A few faint wisps lingered in some images, but the active cloud bands and bright knots that had characterized the planet's appearance for decades had vanished. By 2020, the images showed essentially nothing, a smooth blue sphere, clean, featureless. The cloud factory had shut down. Scientists tracking the solar correlation could connect this to the known pattern. The solar minimum of 2019 to 2020 was deep enough that ultraviolet output had dropped significantly from previous cycles. The cloud seeding mechanism, already weakened by several years of declining solar activity, finally fell below the threshold needed to sustain visible cloud formation. The shutdown was the predicted outcome of the solar cycle correlation. In a general sense, scientists expected lower cloud activity during solar minimum. What surprised them was the completeness of the disappearance. Previous solar minima in the observation record had reduced Neptune's cloud coverage but had not stripped the planet this bare. The 2019 to 2020 solar minimum produced a more severe cloud loss than the cycle alone seemed to predict. This excess cloud loss suggests the solar cycle is not the only factor. Something else may have pushed the cloud abundance below its normal solar minimum floor. The stratospheric cooling trend running since 2003 may have played a role. If the cooling altered the thermal structure of the atmosphere in ways that made cloud formation harder, even with some seed particles present, the combination of solar minimum and thermal change would compound into a more severe disappearance than either factor alone would produce. The interaction between the stratospheric cooling and the cloud disappearance is one of the central unsolved questions in Neptune atmospheric science. Both events happened across the same time window. Both were more extreme than the models predicted. The overlap is too consistent to be coincidence, but the exact causal relationship is not confirmed. And there is a third thread running alongside these two. The same period that saw the clouds vanish and the stratosphere cool was also the period that saw the South Pole spike 20 degrees in 2 years. 3 simultaneous and dramatic atmospheric events, all happening on the same planet in the same decade, each behaving more extremely than the models predicted. 3 events that may share a single cause, or may reflect 3 separate mechanisms all failing at once. Either way, Neptune was telling scientists something important, and the tools needed to fully hear that message were about to come online. Neptune does not announce itself. It sends no radio signal, no beacon, no visible glow. From Earth, it is a faint blue dot that even powerful telescopes struggle to resolve into meaningful detail. To read its temperature, scientists needed instruments capable of detecting something invisible: heat. Every object warmer than absolute zero emits infrared radiation. At absolute zero is roughly negative 459 degrees Fahrenheit, the point where all molecular motion stops. Everything above that temperature, including a planet in the outer solar system, radiates heat outward as infrared light. The colder the object, the longer the wavelength of infrared it emits. Neptune, sitting at temperatures around negative 350 degrees Fahrenheit in its upper atmosphere, emits infrared wavelengths in a specific range called thermal infrared. Human eyes cannot see thermal infrared. Standard cameras cannot detect it, but specialized detectors chilled to extremely low temperatures can. These instruments, mounted on large ground-based telescopes, measure the intensity of thermal infrared light arriving from Neptune after crossing 8 billion miles of space. The challenge is precision. By the time Neptune's thermal infrared signal reaches Earth, it is extraordinarily faint. The signal has spread across an enormous area of space during its journey and dimmed accordingly. Detecting temperature variations of a few degrees across different regions of a distant planet requires instruments capable of reading a signal so weak it would be invisible to any less sensitive detector. To get a sense of the precision required, imagine trying to feel the warmth of a candle flame from 8 meters away. The heat is technically there, spreading outward from the source, but detecting it requires sensors far beyond human skin. The thermal infrared telescopes used to measure Neptune's temperature are doing something roughly analogous, scaled up to planetary distances. The measurement itself involves scanning the planet's disk, the visible circular face, and recording the infrared brightness at each point. Brighter infrared means more heat. Scientists then convert the brightness measurements into temperature values using known physical relationships between infrared emission and temperature. The result is a thermal map showing which parts of the planet are warmer and which are cooler. Across the 2003 to 2020 observation period, scientists assembled 95 such thermal maps. Each one required telescope time at major observatories, careful instrument calibration, and hours of data processing. The full dataset represents roughly 20 years of coordinated effort across multiple institutions and multiple countries. That number, 95 images over 20 years, might sound modest, but building a thermal record of any outer planet at this level of detail is an extraordinary achievement given the distances and instrument requirements involved. Each image required perfect atmospheric conditions at the observatory site, precise telescope pointing, and detectors operating at the edge of their sensitivity limits. The dataset they produced became the most detailed thermal record of Neptune ever assembled, and the story it told was one that no scientist who contributed to collecting it had expected to find. The temperature record revealed a planet's upper atmosphere was behaving in ways that broke every model built to describe it. But thermal infrared data from the ground has limits. Earth's own atmosphere absorbs some of the infrared signal before it reaches the detectors. Weather, humidity, and atmospheric turbulence all introduce noise into the measurements. Ground-based observations, however powerful, carry uncertainty that only space-based instruments can eliminate. And space-based instruments were about to change the picture entirely. 3 observatories on the ground built the foundation of Neptune's temperature record. The Very Large Telescope sits in the Atacama Desert in northern Chile, perched on a mountain called Cerro Paranal at an elevation of about 8,500 feet. The Atacama Desert is one of the driest places on Earth. On many nights, the air above Cerro Paranal contains almost no water vapor. Water vapor absorbs infrared radiation, so dry air is essential for thermal infrared astronomy. The Very Large Telescope's location was chosen partly for this reason. Its instruments can detect infrared signals that would be swallowed by moisture-laden air at lower altitude sites. The telescope itself consists of 4 separate mirrors, each about 27 feet across, that can work together as a single combined instrument. When operating in combined mode, the system achieves a level of detail that would require a single mirror roughly 130 feet wide to match. For Neptune observations, this detail matters. The planet's disk, as seen from Earth, is small enough that resolving individual temperature regions across different latitudes requires every bit of resolution available. On the other side of the Pacific, on the summit of Mauna Kea in Hawaii, at nearly 14,000 feet of elevation, two other major observatories contributed to the Neptune record. The Keck Observatory houses two separate telescopes, each with a mirror about 33 feet across. The Subaru telescope, operated by Japan's National Astronomical Observatory, uses a single mirror about 27 feet across and is equipped with an instrument specifically designed for near-infrared and thermal imaging. Mauna Kea's elevation places it above a significant portion of Earth's water vapor layer. Nights on the summit are bitterly cold, with winds that can shut down operations entirely. The working conditions for the people who run these telescopes are genuinely harsh, but the quality of infrared observations from that altitude is among the best achievable from any ground-based site on Earth. The combination of Chilean and Hawaiian sites gave the Neptune monitoring program geographic diversity. When weather prevented observations from one site, the other might provide a clear window. Over 20 years, the two regions collectively delivered the 95 thermal infrared images that built the full temperature record. Processing those images required correcting for Earth's own atmospheric interference, aligning images taken years apart by different instruments, calibrating the temperature scale consistently across the entire dataset, and separating the signal from noise at multiple stages. Each image went through an extensive reduction pipeline before a usable temperature measurement could be extracted. The researchers who built and maintained this pipeline worked across institutions in the United Kingdom, the United States, and other countries, sharing data and methods over 2 decades. This kind of long-term coordinated monitoring campaign is rare in planetary science. Most telescope time is allocated in short blocks to individual projects. Sustaining a 20-year monitoring campaign requires consistent institutional support and a long-term commitment that is difficult to maintain. The fact that this particular campaign existed at all is partly luck, and what it captured, the full arc of Neptune's atmospheric changes from 2003 through 2020, would have been invisible without it. Without that sustained record, Neptune's story would have stayed hidden, but there was still a gap. Ground-based telescopes, however powerful, operate through Earth's atmosphere. Space had its own tools, and those tools filled in what the ground could not reach. Earth's atmosphere is a filter. It blocks and absorbs certain wavelengths of infrared radiation before they reach the ground. For thermal infrared astronomy, even the best high-altitude observatory sites lose some signal to the air above them. Getting a truly clean measurement requires lifting the instruments above the atmosphere entirely. NASA's Spitzer Space Telescope did exactly that. Spitzer launched in 2003 and spent more than 16 years operating in space, trailing Earth in its orbit around the Sun. Its primary mission was infrared astronomy, the detection of heat signatures from objects across the universe. Its detectors were chilled to temperatures near absolute zero using liquid helium, making them sensitive to infrared signals so faint they would be completely buried in thermal noise at room temperature. For Neptune observations, Spitzer provided something the ground-based telescopes could not consistently deliver: infrared measurements uncontaminated by Earth's atmospheric absorption. The data Spitzer captured gave scientists a cleaner baseline reading of Neptune's thermal emission, which helped calibrate and validate the temperature values derived from ground-based instruments. Spitzer's field of view was not optimized for resolving fine spatial detail across the small angular size of Neptune's disk. It could not map individual temperature regions across the planet with the same precision as the combined power of the Chilean and Hawaiian ground observatories. But its spectral coverage and sensitivity in wavelength, ranges that ground-based instruments struggle with, made it a valuable complement to the overall monitoring campaign. The combination of ground-based and space-based data allowed scientists to cross-check their temperature measurements in a way that reduced uncertainty. If a temperature reading from a ground telescope matched what Spitzer detected in a compatible wavelength range, confidence in the measurement increased. Where the datasets diverged, scientists knew to look more carefully at potential sources of error. Spitzer ran out of liquid helium coolant in 2009, which ended its ability to operate its most sensitive long-wavelength detectors. It continued limited operations in warmer detector modes until NASA retired the mission into 2020. During its operational period, Spitzer contributed multiple observation windows to the Neptune temperature record, bridging gaps where ground-based conditions were unfavorable. The broader lesson from Spitzer's contribution is about the architecture of scientific infrastructure. No single telescope, however powerful, can answer a complex question about a distant planet alone. The Neptune temperature record required a network, multiple ground-based observatories across 2 continents, a space telescope above the atmosphere, and a coordinating team managing the combined data stream across decades. This architecture is expensive. It requires sustained funding, international cooperation, and institutional patience that does not always exist in science. The Neptune monitoring campaign was built and maintained through exactly this kind of sustained effort, and the data it produced revealed something that demanded an even more powerful instrument to fully investigate, one that would see Neptune's atmosphere in a level of detail no previous telescope had ever achieved, one that had only just come online. The number 95 sounds ordinary, a test score, a highway speed, a percentage. As a count of thermal infrared images collected across 20 years of coordinated observation of a planet 2.8 billion miles away, it represents one of the most demanding long-term data collection efforts in the history of outer planet science. Building this dataset required telescope time at some of the most oversubscribed observatories on Earth. Major facilities like the Very Large Telescope and the Keck Observatory receive far more requests for observation time than they can accommodate. Every allocation of telescope time to Neptune came at the cost of some other scientific project that did not get scheduled. The teams running this monitoring campaign competed for their time allocations year after year for 2 decades. Each observation session required precise pointing, careful instrument setup, and the right atmospheric conditions. Thermal infrared imaging at this sensitivity is particularly demanding because the telescope itself and the surrounding environment emit infrared heat that can contaminate the signal. Observers go to extraordinary lengths to isolate the target signal from background thermal noise using specialized optical designs, detector shielding, and careful calibration procedures. After each session, the raw data went through a reduction pipeline. Raw infrared images contain instrumental artifacts, atmospheric distortion, and electronic noise layered over the real signal. Removing these contaminants without introducing new errors requires software built specifically for each instrument and regularly updated as understanding of the instrument's behavior improves. The final temperature measurement extracted from each image carries an uncertainty range. Scientists are not reading Neptune's temperature as a single exact number, they are reading it as a range. For example, -340 degrees Fahrenheit, plus or minus 4 degrees. The width of that range depends on the quality of the observation, the precision of the calibration, and the level of atmospheric interference. Across 95 images, the individual uncertainties average out. The trend signal, the consistent long-term change in temperature, emerges more clearly as the number of data points grows. A single measurement showing an unusually cold temperature could be a real event or an instrument glitch. A 15-year trend of consistently falling temperatures confirmed across multiple instruments at multiple sites is real. This is why the study took so long to publish. The researchers needed enough data points to be confident the trend was real and not an artifact of measurement error. They needed the full arc of the temperature curve, not just the first decade of it, before they could characterize what was happening. When the comprehensive study was published in 2022, it presented not just a temperature record, but a fundamental challenge to existing models of ice giant atmospheric dynamics. The models had failed, the data had spoken, Neptune's atmosphere was doing something the best planetary science available could not predict, and understanding why required filling in the chemical picture of what was actually happening inside that atmosphere, a picture that 95 thermal infrared images alone could not complete. The next generation of instruments was built for exactly that task, and one of them was already turning toward Neptune. Neptune receives very little energy from the Sun at 2.8 billion miles away. The sunlight arriving at Neptune carries roughly 900 times less energy per square foot than the sunlight hitting Earth. Scientists long assumed that a planet this far from its star would be almost entirely dependent on that faint solar input to stay warm. Neptune corrected that assumption completely. Measurements of Neptune's energy budget reveal that the planet radiates more than twice as much heat into space as it receives from the Sun. The difference is enormous. Neptune is not just reflecting solar energy back outward, it is generating its own internal heat and pumping it into space at a rate that dwarfs the solar contribution. This internal heat source has been known since Voyager 2's flyby confirmed it in 1989, but its origin remains one of the deeper mysteries of Neptune's science. The leading explanation is that Neptune is still slowly cooling from the heat generated when it formed roughly 4.5 billion years ago. Planet formation involves enormous collisions between rocky and icy bodies accumulating under gravity. Those collisions release tremendous heat. A planet as massive as Neptune takes billions of years to radiate that formation heat away. But the math does not work out cleanly. The rate at which Neptune sheds internal heat suggests either that its formation was unusually energetic or that an additional ongoing process is generating heat deep inside. One candidate is the slow separation and settling of heavier materials toward the planet's core, a process called differentiation. As denser materials sink inward through Neptune's interior over geological timescales, they release gravitational energy as heat. This process is ongoing and provides a steady internal heat source. The internal heat output matters for understanding the temperature changes scientists observed between 2003 and 2020. The stratospheric cooling they measured is happening in the upper atmosphere, far above the region where internal heat originates. But internal heat drives convection in the lower atmosphere, and convection shapes the thermal structure of the layers above it. If something changed in how Neptune's internal heat moved through its lower atmosphere and into the stratosphere, it could influence the stratospheric temperatures scientists were measuring. Nobody has confirmed whether internal heat transport changed during the observation period. The lower atmosphere is far harder to measure than the stratosphere. The instruments used to build the temperature record were sensitive to stratospheric altitudes, but had limited visibility into the deeper weather layer where internal heat enters the atmospheric system. This gap in the data is significant. The stratosphere is the visible tip of a far deeper and more complex thermal system. The temperature changes documented at the top may reflect processes happening far below that the observation tools were not designed to see. Understanding Neptune's full energy budget, the interplay between solar input, internal heat, and atmospheric radiation requires measurements at depths that existing instruments cannot reach. But other discoveries about Neptune's deep interior have revealed processes so extreme they seem impossible. What happens deep inside Neptune, under pressures that crush matter into forms that cannot exist anywhere else, turns out to be one of the strangest chapters of this planet's story. Deep inside Neptune, it rains diamonds. This is not a metaphor. Experimental physics and computational models both support it. Under the extreme pressures and temperatures found deep within Neptune's interior, carbon atoms get squeezed together so tightly that they bond into diamond crystal structures, forming solid gems that fall through the liquid interior like rain falling through air. The pressure required to make this happen is almost beyond imagination. At Neptune's surface, if it had a solid surface, you would already feel a pressure far beyond anything survivable. But the crushing weight of the atmosphere above pushes down with increasing force at every level deeper into the planet. By the time you reach the depths where diamond formation occurs, you are under pressures millions of times greater than the pressure at Earth's sea level. Under those conditions, carbon, which exists in Neptune's interior as part of methane molecules that got broken apart by heat and pressure, can no longer exist in its normal molecular form. The atoms get forced into the rigid crystalline lattice structure of diamond. Groups of these carbon atoms bond together, forming small diamond crystals. And because diamonds are denser than the surrounding material, they sink. They fall inward toward Neptune's core. Scientists confirmed this process in laboratory experiments by using powerful lasers to recreate the extreme pressure and temperature conditions of Neptune's interior inside a tiny chamber. They fired intense laser pulses at a plastic material that mimics Neptune's hydrocarbon-rich interior composition. The lasers compressed and heated the target so rapidly that, for a fraction of a second, the conditions inside the chamber matched those deep inside Neptune. Instruments detected the formation of diamond-structured carbon within that brief window. The experimental confirmation came from researchers at multiple institutions and has been replicated. Diamond rain in ice giant interiors is now one of the more confidently supported exotic phenomena in planetary science. The diamonds forming inside Neptune are not the kind you could hold in your hand. They likely form as tiny crystals or clusters of crystals, though some models suggest they could grow larger over time as they fall through the interior. A proposed scenario involves the diamonds eventually reaching a region near the core where conditions change, causing them to dissolve back into the surrounding material or pool at the core boundary. Some researchers have speculated that diamond accumulation near Neptune's core might contribute to the planet's internal heat generation, as the settling of dense material releases gravitational energy. If true, diamond rain would be directly connected to the planet's energy budget, and indirectly to the atmospheric temperature changes scientists observed at the surface. That connection is speculative. The interior of Neptune is entirely inaccessible to direct observation. No instrument has ever entered Neptune's atmosphere, let alone reached its deep interior. Everything known about conditions down there comes from physics calculations, laboratory experiments, and computer simulations. But the physics is solid. Under those pressures, carbon behaves that way. The diamonds are falling inside Neptune right now, even as scientists on Earth try to understand why its clouds disappeared. And the diamonds are not even the most extreme thing happening on this planet. If you stepped outside on Neptune, you would be dead before you could register what was happening. The winds at Neptune's cloud tops reach speeds of up to 200 miles per hour. To put that in human terms, a commercial airplane cruises at roughly 550 miles per hour. Neptune's winds move more than twice that fast. A passenger jet sitting in those winds would be torn apart and scattered across the atmosphere in seconds. 200 miles per hour is the fastest wind speed recorded on any planet in the solar system. Not the fastest gust ever measured in a localized storm, but the sustained, large-scale wind speed characterizing the planet's general atmospheric circulation. Neptune's entire outer atmosphere is moving at this velocity, organized into massive jet streams that circle the planet. The winds blow in a direction opposite to Neptune's rotation. Neptune spins from west to east, the same as Earth, but the main wind patterns in its atmosphere flow from east to west against the spin. This retrograde wind pattern is something scientists still find difficult to explain. On Earth, the relationship between the planet's rotation and its atmospheric circulation is complex but broadly aligned. Neptune's counter-rotating winds represent a different kind of atmospheric engine, one driven by forces that do not have a clean parallel in Earth-based meteorology. The energy source for these winds is not straightforward. On Earth, most wind energy ultimately comes from solar heating driving atmospheric circulation, but Neptune receives almost no solar energy compared to Earth. The energy driving 200 mile per hour winds across a planet the size of nearly 60 Earths has to come largely from Neptune's internal heat. Internal heat drives convection, warm material rises, cool material sinks. On a rotating planet, this convection gets organized by the planet's spin into large-scale wind patterns through a process called the Coriolis effect. Neptune's combination of intense internal heat, rapid rotation, and the unique dynamics of its deep hydrogen and helium atmosphere appears to drive wind systems far more powerful than anything the planets closer to the Sun can generate. The winds also shaped what scientists observed in the cloud record. During years when Neptune had active cloud cover, the clouds moved visibly across the planet's disk between observations. The rate of that movement gave scientists a way to measure wind speeds indirectly from telescope images. Some of those cloud-tracking wind measurements helped confirm the 200 mph figure. When the clouds disappeared, scientists lost that wind tracking tool as well. A cloudless Neptune was not just visually featureless, it was instrumentally quieter. The visible markers that helped scientists read the atmosphere's dynamics had been removed. The wind speed record also connects back to Neptune's temperature crisis. Atmospheric dynamics, heat distribution, and wind patterns are all linked. A planet whose thermal structure changed as dramatically as Neptune's did between 2003 and 2020 would almost certainly have experienced changes in its wind patterns as well. Those changes are much harder to measure without cloud features to track, but wind speed is stable. It's part of Neptune's deep character. What changed were the clouds and the temperatures above them, and what had existed before all of it changed was one of the largest storms ever observed in the solar system. In 1989, Voyager 2 flew past Neptune and captured an image that immediately drew comparisons to Jupiter's famous Great Red Spot, a massive dark oval storm system spinning in Neptune's southern hemisphere. Scientists named it the Great Dark Spot. The Great Dark Spot was roughly the size of the entire Earth, a storm wide enough that if you placed our whole planet inside it, the edges would not reach the walls. It rotated counterclockwise and moved westward across Neptune's face. Companion clouds of bright methane ice formed along its edges and interior, churning with the storm's circulation. Voyager 2's images made it one of the most striking objects ever photographed in the solar system, a dark void in the blue of Neptune, fringed by white, massive beyond anything that exists on Earth. 5 years later, the Hubble Space Telescope looked for the Great Dark Spot. It was gone. A storm large enough to contain Earth had simply disappeared in less than 5 years. In its place, a new dark spot had formed in Neptune's northern hemisphere. This northern storm was not there when Voyager 2 flew past. It had appeared between 1989 and 1994. The behavior of Neptune's storm systems defies the patterns seen on other planets. Jupiter's Great Red Spot has persisted for at least 350 years, a storm that has outlasted entire human civilizations. Saturn's storms are long-lived. Earth's hurricane systems are temporary, but follow understood formation and decay cycles. Neptune's storms seem to appear and vanish on timescales of years. Large, powerful, then gone, replaced by new ones elsewhere. The mechanism driving this rapid turnover is connected to the same atmospheric dynamics that make Neptune so difficult to model: the interplay between internal heat, rapid rotation, cold upper atmosphere, and fast wind systems. Scientists believe Neptune's dark spots form when material from the lower atmosphere rises into the upper atmosphere and gets organized into a rotating vortex by the planet's wind patterns. The spots are essentially holes or disruptions in the bright methane cloud layer, revealing the darker atmosphere below. When conditions change, perhaps driven by shifts in the wind patterns or thermal structure, the organizing force sustaining the vortex weakens and the storm breaks apart. The Great Dark Spot's disappearance before Hubble arrived is one of the more dramatic examples of how quickly Neptune can change, and it raises a question relevant to the temperature crisis. If Neptune's visible atmosphere can reorganize completely in 5 years, reshuffling its storm systems from hemisphere to hemisphere, then the changes in cloud cover and stratospheric temperature documented between 2003 and 2020 are perhaps less surprising. Neptune changes fast, faster than any model built before the monitoring campaign predicted. And beyond the storms, beyond the winds, and the temperature swings, the planet carries other features that most people never hear about. Saturn's rings are famous, wide, bright, visible through a backyard telescope. They define the public image of a ringed planet. Jupiter has a faint ring system barely detectable. Uranus has rings, discovered in 1977. Neptune has rings too, and they are among the strangest in the solar system. Neptune's rings were discovered in 1984, 5 years before Voyager 2 arrived to photograph them directly. The discovery came through a technique called stellar occultation, which involves watching a distant star and measuring what happens to its light as a planet passes between the star and Earth. If the planet has rings, the rings block the starlight momentarily before and after the planet itself obscures the view. The occultation data from Neptune produced something unexpected. The starlight dips before and after the planet's passage were not symmetric. The rings blocked the star's light on one side of the planet, but appeared incomplete or absent on the other side. This suggested Neptune's rings were not continuous bands all the way around the planet. They were arcs, partial rings, clumped material covering only portions of their orbital paths. Voyager 2 confirmed the arcs in 1989. It photographed 5 main rings surrounding Neptune, all faint and dark compared to Saturn's brilliant ice rings. 3 of the 5 rings contain denser clumps of material called ring arcs, named after ideals like liberty, equality, and fraternity. These arcs contain concentrations of ring particles thick enough to show up clearly in images, while the rest of the ring in between them is much thinner and dimmer. The arcs have a stability problem. Orbital mechanics predicts that material in a ring should spread out over time. Particles moving at slightly different speeds in adjacent orbits will gradually diffuse, spreading the clump material around the entire ring. A ring arc should smooth itself out into a uniform ring within a few thousand years by standard calculations. Neptune's ring arcs have existed for at least decades based on observations, and possibly much longer. Something is keeping the material clumped. The leading explanation involves gravitational resonance with one of Neptune's inner moons. A moon orbiting at just the right distance creates a gravitational rhythm that pushes ring particles into specific zones and keeps them there, like a cosmic fence corralling material into arcs rather than letting it spread freely. Neptune's small moon Galatea orbits just inside the main ring arc region and is the primary candidate for this shepherding role. The ring arcs are made of dark material, likely a mixture of ice particles coated with carbon-rich compounds darkened by radiation exposure over billions of years. Their dark color is why they are so much harder to see than Saturn's bright ice rings. They absorb light rather than reflecting it. Voyager 2 images from 1989 showed the arcs clearly. More recent observations with Hubble and ground-based telescopes have tracked changes in the arcs over the following decades. Some portions have brightened or dimmed. The arcs appear to be evolving, possibly due to collisions between ring particles, ongoing shepherding dynamics, or material exchange with nearby moons. The rings are another reminder that Neptune carries complexity in every layer of its system, from the deep interior where diamonds fall, through the turbulent atmosphere where storms vanish and clouds disappear, out to the faint arcs of dark debris orbiting silently in the cold beyond. Neptune is blue, not sky blue or ocean blue or the blue of a flame, a deep, rich, saturated blue that looks almost painted on in telescope photographs. It is one of the most visually striking colors in the solar system, and it comes entirely from a single gas, methane. Methane is colorless to human eyes in the amounts found on Earth. Natural gas burned in a stove is mostly methane, and the flame it produces burns blue-orange, but the gas itself is invisible. On Neptune, methane exists in the atmosphere at concentrations high enough to produce a visible color effect through a process called selective absorption. White light from the sun contains all wavelengths of visible light, from violet at one end of the spectrum to red at the other. When sunlight enters Neptune's atmosphere, methane gas absorbs the red wavelengths preferentially. Red light gets captured by methane molecules and converted to heat. But blue and violet wavelengths pass through methane with minimal absorption and get reflected back outward from the deep atmosphere. The result is that the light bouncing back from Neptune toward a distant observer has lost its red component. What reaches your eye is a light spectrum weighted heavily toward blue. Neptune looks blue because methane has filtered out the red. Uranus, Neptune's neighbor in the outer solar system, also contains methane in its atmosphere and is also blue-green in color. The two planets are similar in size and composition, but Neptune is a distinctly deeper, richer blue than Uranus, and scientists spent years trying to explain why two similar planets look different. A partial answer emerged from more detailed spectral analysis. Uranus and Neptune both have methane, but their atmospheric structures differ in ways that affect how light scatters and reflects. A haze layer at high altitude in Uranus's atmosphere appears to add a greyish tint that lightens its overall colour toward green-blue. Neptune's upper atmosphere has less of this haze, or a different distribution of it, allowing the deeper blue from methane absorption to dominate. The photochemical processes connected to Neptune's cloud story also play a role here. The same ultraviolet-driven reactions that produce cloud seeds generate haze particles in the upper atmosphere. Changes in solar activity change the production rate of those haze particles. A change in haze concentration would subtly affect how Neptune's colour appears to telescopes. This means that the same solar cycle driving Neptune's cloud disappearance may also be slowly changing its colour at a level that precise spectral instruments can detect. Scientists are investigating whether the optical properties of Neptune's atmosphere shifted during the cloud disappearance period in ways consistent with changes in upper atmospheric haze. The colour of a planet is not just aesthetic information, it is a chemical record. Neptune's specific shade of blue encodes information about methane concentration, haze particle density, and the structure of the atmosphere at different altitudes. Reading that colour carefully is another way to track the same changes that thermal, infrared measurements detect as temperature variations. Two completely different tools, one measuring colour and one measuring heat, pointing at the same planet and telling parts of the same story. And that story was about to reach consequences far beyond Neptune itself. Neptune's atmospheric crisis matters far beyond Neptune. Astronomers trying to understand planets around other stars face a fundamental challenge. They cannot visit those planets. They cannot land instruments on them. They cannot fly a spacecraft past them the way Voyager 2 flew past Neptune. Everything they know about exoplanets comes from light, from the faint signals that distant worlds leave on the light coming from their parent stars. The most common planet type discovered orbiting other stars is something called a sub-Neptune, a planet larger than Earth but smaller than Neptune. These worlds do not exist in our solar system, but they appear to be the most abundant planet type in the galaxy, based on data from the Kepler and TESS space telescopes. Understanding how their atmospheres behave is one of the central goals of modern astronomy. Neptune and Uranus, our local ice giants, serve as the closest models available. When astronomers try to predict what the atmosphere of a sub-Neptune exoplanet looks like, how thick it is, what gases it contains, how its temperature varies with altitude, they draw heavily on ice giant science. Neptune is the template. If that template is wrong, every model built from it is wrong too. The discovery that Neptune's atmosphere behaves in ways that existing models cannot predict creates a real problem for exoplanet science. Scientists cannot currently explain why Neptune's stratosphere cooled 14 degrees during summer, or exactly why its clouds vanished, or why its south pole spiked 20 degrees in 2 years. The mechanisms are unclear. The models are broken. Using a broken Neptune model to interpret the spectra of exoplanets orbiting distant stars introduces errors that compound at every step of the analysis. If scientists misidentify atmospheric features in an exoplanet spectrum because their baseline model for how ice giant atmospheres behave is wrong, they could misclassify the planet's composition, temperature, structure, or potential habitability. This is not a theoretical risk. Researchers using the James Webb Space Telescope to analyze exoplanet atmospheres are doing so right now. The interpretive frameworks they use draw on planetary models that Neptune has just shown to be incomplete. Knowing that those frameworks have gaps is important. The solar cycle influence on Neptune's cloud chemistry is a specific example of a mechanism that was not included in standard atmospheric models. If that mechanism operates on exoplanets orbiting stars with their own activity cycles, it could produce atmospheric changes that observers misinterpret as evidence of different chemical compositions or different temperatures. Neptune has essentially issued a correction to the instruction manual for reading planetary atmospheres. The correction is incomplete because scientists do not yet fully understand what Neptune is showing them. But the existence of the correction is now undeniable. Understanding what Neptune is doing in full detail is a prerequisite for understanding the billions of similar worlds scattered across the galaxy. and the tools to begin that fuller understanding are already running. When the Kepler Space Telescope surveyed a patch of sky containing roughly 150,000 stars between 2009 and 2018, it found thousands of planets. The distribution of those planets by size told a story that surprised planetary scientists. The most common planet type was the sub-Neptune. Planets between 1.5 and 4 times Earth's size, too large to be rocky worlds like ours, too small to be gas giants like Jupiter. They appear around roughly 30 to 50% of Sun-like stars. They are statistically the dominant planet type in the galaxy. Our solar system has none. Earth is a rocky planet, Jupiter is a gas giant, Uranus and Neptune are ice giants at the larger end of the sub-Neptune size range. Whatever produces sub-Neptunes in such abundance around other stars apparently did not produce them here, or produced our ice giants at the edge of the sub-Neptune category, and nothing smaller. This gap is one of the stranger features of our solar system when viewed against the galactic average. We live in a system that lacks the most common planet type in the universe. And because we lack them locally, we have no close-up examples to study. No mission has ever visited a true sub-Neptune. Everything known about them comes from the signals their atmospheres leave on starlight. Neptune is the closest analogue in our local neighbourhood, an ice giant at the upper end of the sub-Neptune size range, with a hydrogen-dominated atmosphere, methane chemistry, and a complex thermal structure. If you want to understand how a sub-Neptune behaves, Neptune is the best starting point available. But Neptune has just revealed that even it behaves in ways science cannot fully explain. The atmospheric changes documented between 2003 and 2020 exposed gaps in the models used to describe ice giant atmospheres generally. If Neptune, which scientists have been watching up close for decades and flew a spacecraft past in 1989, still produces dramatic surprises, then the sub-Neptunes orbiting other stars are almost certainly hiding behaviors our models have not anticipated. This is humbling at a specific level. Astronomers report exoplanet atmospheric compositions and temperature structures with considerable precision based on spectral analysis. The error bars on those measurements are often tight, but the systematic errors introduced by using incomplete planetary models are harder to quantify and may be significantly larger than the measurement uncertainty scientists typically report. Neptune's crisis has forced a reckoning. The models need rebuilding. The assumptions need revisiting. The next generation of ice giant science, informed by better observations of Neptune and Uranus, and driven by the data needs of exoplanet research, has to produce a more accurate picture. The James Webb Space Telescope is already contributing to that rebuilding process, and what it has been able to see in Neptune's atmosphere represents a genuine step forward in the science of distant worlds. The James Webb Space Telescope launched in December of 2021. After a 6-month deployment and calibration process, it began science observations in mid-2022. Within its first year of operation, it turned toward Neptune. Webb's primary mirror is about 21 feet across, nearly 3 times wider than Hubble's, but size alone does not explain Webb's power for Neptune science. The telescope is optimized for infrared wavelengths, the same part of the light spectrum that carries heat information from planetary atmospheres. Its detectors can resolve wavelength features in infrared spectra with a precision that allows scientists to identify specific molecules in an atmosphere and measure their concentrations. The first Webb images of Neptune, released to the public in late 2022, showed something Hubble had never captured with this clarity. The planet's faint ring system visible alongside the planet itself, and a sharp new view of the polar region. The images alone demonstrated what Webb's infrared sensitivity could see that previous instruments could not. But the science value went deeper than the images. Webb's spectroscopic instruments can analyze the composition of Neptune's upper atmosphere by measuring which infrared wavelengths the atmosphere absorbs and emits. Different molecules absorb at different wavelengths. By mapping the absorption pattern, scientists can identify which gases are present and roughly how abundant they are. This is the chemical fingerprint that scientists needed to investigate the mechanisms behind Neptune's temperature changes. If methane concentrations changed between 2003 and 2020 in ways that altered the stratosphere's ability to retain or release heat, Webb can detect the current methane levels and compare them to historical estimates. If other gases, such as hydrogen cyanide or ethane, shifted in concentration, those shifts would appear in Webb spectra. The polar stratosphere is a particular target. The 20-degree spike at the South Pole left a question about what is happening there chemically. A warm polar stratosphere would change the vertical distribution of gas species. Gases that condense at lower temperatures might remain as vapor higher up. Photochemical products might accumulate differently in the warmer zone. Webb's sensitivity is sufficient to detect these compositional differences between the polar region and the surrounding atmosphere. Scientists also hope Webb observations over the coming years will track how the atmosphere evolves as Neptune moves deeper into southern hemisphere. Summer. The South Pole is still in summer. The global cooling trend status after 2020 is not yet fully documented. Whether the polar spike was a one-time event or the beginning of a longer warming trend is a question Webb's sustained monitoring can eventually answer. Webb's lifetime is estimated at roughly 20 years based on fuel reserves used for its orbital positioning. For Neptune science, 20 years of Webb observations would cover roughly half of one Neptunian season, a more meaningful fraction of the full seasonal cycle than previous instruments achieved. Every year of Webb data on the ultimate record that could, over time, reveal the full structure of the atmospheric changes that began in 2003. The complete answer may take decades, but the tools to find it are now running, and beneath all the observations, all the data, all the instruments pointing across billions of miles, lies a set of questions that science has not yet answered. The study published in 2022 presented the temperature record clearly: 14 degrees of global stratospheric cooling over 15 years, 20 degrees of polar warming in 2 years, a 26-year cloud disappearance, a strong correlation between the solar cycle and cloud abundance. What the study could not present was a complete causal explanation. The solar cycle correlation is well supported by the data. The mechanism of ultraviolet-driven photochemical cloud seeding is physically grounded and consistent with what is known about atmospheric chemistry. Scientists are reasonably confident that solar activity influences Neptune's cloud cover. What remains unconfirmed is the connection between the solar cycle and the deep stratospheric cooling. The 11-year solar rhythm is too short and too cyclical to fully account for a 15-year continuous cooling trend. Solar minima come and go every 11 years. A cooling trend that spans 15 years without reverting during an intervening solar maximum requires either a longer period solar variation, an atmospheric chemical shift that persisted across multiple solar cycles, or a separate mechanism entirely. The candidates for that separate mechanism include changes in atmospheric methane concentration, changes in another heat-active gas, changes in internal heat transport from the lower atmosphere, and long-period internal atmospheric variability operating on Neptune's own decadal timescales. Each of these is physically plausible, none of them is confirmed. The data needed to distinguish between them requires chemical composition measurements at stratospheric altitudes over a sustained period, measurements that only Webb and future instruments can provide. The polar spike adds another unresolved layer. Scientists proposed that accumulated solar energy at the pole during the summer season might have released rapidly, but the mechanism for storing and then suddenly venting atmospheric energy in a localized region is not fully described. The polar chemistry during the spike period is unknown. The pre-spike conditions in the polar stratosphere are poorly documented. There is also a timing puzzle. The polar spike happened between 2018 and 2020. The global stratospheric cooling reached its minimum around 2018. Both events reached their peak intensity at roughly the same time. A connection between these two events, one cooling globally and one warming locally at exactly the same moment, seems almost too precise for coincidence. But the physical link, if one exists, is not established. Some planetary scientists have proposed that the global cooling may have driven atmospheric circulation changes that concentrated heat at the pole, a kind of compensation effect where heat removed from the global stratosphere was funneled into the polar region. This mechanism is speculative. It would require atmospheric dynamics that existing models do not capture. Neptune keeps offering data that points toward a deeper architecture in its atmospheric system, an architecture where solar input, internal heat, atmospheric chemistry, and large-scale circulation interact in ways that produce behaviors far more complex than any single-factor explanation can capture. The honest scientific position is that the full picture is not yet drawn. The data is real, the questions are sharp, the answers are in the future, and one wild card in that future involves two gases that most people have never considered in relation to a distant planet's temperature. Deep in Neptune's atmosphere, two gases shape the planet's thermal personality more than any other: methane and molecular hydrogen. Methane's role in Neptune's color and cloud formation is well established. Its role in the planet's thermal balance is less discussed, but equally important. Methane in Neptune's stratosphere absorbs infrared radiation and re-emits it. The net effect depends on altitude and concentration. At certain altitudes, methane warms the surrounding air by absorbing incoming solar infrared. At other altitudes, methane contributes to cooling by emitting infrared heat outward into space more efficiently than surrounding gases. The balance between methane's warming and cooling effects in the stratosphere is sensitive to concentration. A relatively small change in how much methane exists at a particular altitude could shift the stratosphere from a net heat-retaining layer to a net heat-releasing one. If methane concentrations at key stratospheric altitudes decreased between 2003 and 2018, the stratosphere would have become better at radiating heat into space, which would explain the cooling trend. Why might methane concentrations change? The same photochemical reactions that produce cloud seeds also destroy methane. Ultraviolet radiation breaks methane molecules apart, turning them into more complex compounds that drift out of the stratosphere over time. The rate of this destruction depends on solar ultraviolet intensity. If solar activity, and thus ultraviolet output, declined going into a solar minimum, the methane destruction rate would slow, which would increase methane concentrations and likely produce warming, the opposite of what was observed. This suggests methane alone cannot explain the cooling through this direct mechanism, but atmospheric chemistry involves dozens of interacting species. Methane breakdown products feed into the creation of other compounds, some of which absorb heat differently than methane itself. The net effect of changing methane photochemistry on stratospheric temperature involves a chain of reactions that has not been fully modeled for Neptune. Molecular hydrogen plays a different role. It is the dominant component of Neptune's atmosphere and controls the basic thermal properties of the atmospheric gas. Hydrogen can exist in two forms that differ in how the two atoms in each molecule spin relative to each other. These forms are called orthohydrogen and parahydrogen. The two forms absorb and emit heat differently at very low temperatures. The balance between them in Neptune's atmosphere affects how efficiently the stratosphere radiates heat into space. Temperature itself influences which form of hydrogen is more stable. As Neptune's stratosphere cools, the balance between orthohydrogen and parahydrogen shifts. This shift changes the stratosphere's radiative properties, potentially causing it to radiate heat even more efficiently, which in turn causes further cooling. A self-reinforcing cooling loop, where initial cooling drives a hydrogen state change that drives more cooling, could explain both the speed and the persistence of the temperature drop. This feedback mechanism is physically grounded and has been proposed in the scientific literature as a contributor to the stratospheric cooling. Whether it is the primary driver, a contributing factor, or a minor effect is unknown. The measurements needed to test it require precise spectroscopic observations of the orthohydrogen and parahydrogen ratio in Neptune's stratosphere across different latitudes and over time. Webb's infrared spectrometers may be capable of detecting this ratio. The data may already exist in Webb's archived observations, waiting for analysis. The answer to Neptune's cooling mystery may already be recorded. It just has not been extracted yet. Every time humans have assumed the outer solar system was stable, predictable, and behaving according to understood rules, the outer solar system has proven us wrong. Neptune's changes between 2003 and 2020 are the latest and most dramatic correction. A planet 2.8 billion miles away, receiving almost no sunlight, operating on a seasonal cycle that outlasts human lifetimes, managed to cool its global stratosphere by 14 degrees, spike its south pole temperature by 20 degrees in 2 years, and erase every cloud from its face, all within a single generation of human observation. All while existing planetary models said none of it should happen at the speed and scale it did. The implications are broad and honest in their uncertainty. For Neptune itself, scientists now know the atmosphere is a far more dynamic and sensitive system than previous models captured. The interactions between solar ultraviolet input, atmospheric chemistry, internal heat transport, and large-scale circulation create behaviors that cannot be predicted from simple seasonal models. Neptune's atmosphere responds to the Sun's 11-year cycle across 2.8 billion miles in ways that directly affect its most visible features. It generates temperature contrasts between its pole and its surrounding atmosphere that have no clear precedent in the outer solar system. It carries internal heat that exceeds its solar input by more than double, a reservoir of energy that shapes every layer of its atmospheric behavior in ways still being mapped for ice giant science. More generally, Neptune has revealed that the models built on Earth-based atmospheric physics and gas giant observations are missing key mechanisms. The two mechanisms most urgently needed are a complete description of photochemical cloud seeding sensitivity to the solar cycle and a full accounting of how internal heat interacts with stratospheric chemistry at the relevant altitudes. Both require data that only the next generation of instruments, Webb, and eventually a dedicated ice giant mission can provide. For exoplanet science, Neptune's story has drawn a sharp line under a fundamental uncertainty. Billions of sub-Neptune planets orbit stars across the galaxy. Those planets are interpreted through models that Neptune has just shown to be incomplete. Every atmospheric spectrum analyzed with those models carries an unquantified systematic error whose size depends on how wrong the models are. Fixing that error requires understanding Neptune first. And for the human relationship with the solar system more broadly, Neptune is a reminder that familiarity is not the same as understanding. Humans discovered Neptune in 1846. A spacecraft flew past it in 1989. Generations of astronomers have watched it through telescopes. And yet, in the span of roughly 17 years, it managed to surprise the entire scientific community with changes no one predicted, and that remain only partially explained. The solar system is not a finished picture. It is an ongoing process. Planets at its edge behave on timescales longer than scientific careers and through mechanisms that require decades of sustained observation to detect. Neptune's been there for 4.5 billion years. Humans have been paying serious attention for less than 40. The gap between those numbers is where the remaining mysteries live, and the James Webb Space Telescope is staring straight into that gap right now.